All right, so today we're going to be covering L'Hopital's rule. Okay. L'Hopital's rule. L'Hopital's rule is named after a mathematician by the name of L'Hopital. It is not La Hospital. Okay. All right. Try and keep that one a little bit straight. L'Hopital's rule is used when you're dealing with a limit, when you're finding a limit. Of an indeterminate form. Now there are many indeterminate forms, but the one that L'Hopital's addresses is when you're dealing with a ratio. Oh, excuse me. And this limit, when we apply the limit to it, goes to one of the following forms, either 0 over 0 or infinity over infinity. Okay? So we're dealing with a rational function going to a limit where it leads to something 0 over 0. Now there are other indeterminate forms, okay? I just left my piece of paper over here. Hold on. Here there. Okay, some other indeterminate forms are infinity times 0, infinity minus infinity, all of those are indeterminate forms. However, L'Hopital's rule does not apply to any of those. That does not mean that you cannot solve forms like that with L'Hopital's rule. It just means that you've got to manipulate the living daylights out of it so that it looks like f of x over g of x. Okay? So these forms all require manipulation. Okay? Now, some of those other indeterminate forms we can kind of put our brain around as to why they don't make sense. Okay, like for example, we've known that 0 to the 0th, anything to the 0th power is 1 except, okay, think about something. I mean, if you have, and you write it no times, that doesn't mean that you have something all of a sudden. Okay, like for example, if you're going to the supermarket shopping list, corn, 2 bags of potatoes, and no fish. That does not mean that you no longer have a list, right? You just omit writing it, okay? The list still exists, it just doesn't include something. 0th, if we looked at all of the numbers, anything 0th is 1, but nothing to the nothing shouldn't be 1, right? And in fact, what the heck would it be? Could it be, well, 0 written 0 times, then again, it's like, you know, here, take a look, I've got a box. And inside the box is nothing. How much is in there? Well, how do you know? You can't go inside the box to find out. So how do you know if I'm telling you the truth? See, it's kind of like, you know, if I have nothing and I give it to 100 people, they each get nothing. But if I have nothing and I give it to nobody, how much does everyone get? Think about that. If I have nothing and I give it to nobody, how much do everyone get? Well, who is they? Who is they? Who is everyone if there is no one?
I'm not in TOK.
Okay, right, okay, we're not in TOK. Moving on. All right, now this one, okay, infinity to the zeroth. Now, that's another one that's kind of weird, because if you think about it, we have something that's getting very, 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 very big. But we write it no times. How do you, let's put your brain around that one for a minute. It's like it's growing bigger, but then there's something that's making it smaller. Because if you were to, like, say, for example, let's just say you have a to the b, and a is getting bigger, but b is getting smaller. It just depends upon which one grows faster. If you're going to zero faster than you're going to infinity, then you're not going to go to zero. So the question is, who grows faster? Well, since you don't know, you can't say. It's an indeterminate form. There is no value assigned to it, infinity to the zeroth. Okay? Notice 0 to the infinity is not an indeterminate form, because that's 0 times itself 100 times. We have something going to 0, and we multiply it by itself, then we have another thing that's also going to 0. Okay? If we have something getting smaller, and then it's getting smaller and smaller, it's still getting smaller. So it goes to 0. But 1 to the infinity, that's one to put your brain around. Why is 1 written an infinite number of times, not 1? A little weird. Let's think of it this way. Here's a cool example. Imagine you're on a circular road. Okay? We're on a circular road. Okay, this is a bird's eye view of the road that you're walking on. Okay? Things that are and every value on that black circle is 1. Things that are smaller than 1 are inside the circle, and things that are bigger than 1 are outside the circle. Okay? Does this make sense? So it's almost kind of like you were on like on a ring inside a cone, where things are getting smaller on the inside and things are getting bigger on the outside. Okay? All right, so you're walking along this road. Now, if you think about it for a moment, what's happening is let's take this road again and shrink the road. Well, now what's happened is that I'm saying that my road contains only 1, and the values that are to its left, if you think about, if I have 0.9 and I multiply it times itself, what happens to it? Does it get bigger or smaller? 0.9. It gets smaller. All right. What about 0.99? Does that converge or diverge when I multiply it by itself an infinite number of times? Does it converge to 0 or does it diverge to infinity? Does it get bigger or bigger or does it get smaller and smaller? Smaller and smaller. Imagine your high bounce ball example going back to geometric series a million years ago, last year, where you had that high bounce ball and it dropped and it hit the ground and it came up 99% of its original height. All right, and we allowed this to happen over and over and over and over again. The ball eventually gets smaller, its height gets lower and lower and lower and lower and lower until an infinite number of steps later, it's at 0. Okay. Now, what if we had a number just outside of this circle? So 1.1. If I square that, what happens?
Bigger.
It gets bigger. And if I put it to the infinite power, it grows and grows and grows and grows and grows until eventually it goes to what?
Infinity.
Infinity. So we have convergent things inside and divergent things outside. Okay? So what's happening now is that if you're walking along this road, things on the left of you are shrinking to 0, and things to the right of you are exploding. And now, we make it even thinner. So that now you're walking along a very, very narrow little road where things on your right are exploding infinitely high, and things that are to the left of you are shrinking infinitely fast. And then finally, you're standing on no road. There's no more road left. It's infinitely thin. It's now a geometric line, a geometric curve. And on one side of me, it is exploding to infinity. An infinitely small step to the right of this road, boom, right to infinity. And an infinitely small step to my left, boom, right down to zero. I have a left-hand limit and a right-hand limit. One's going to infinity and one's going to zero. Which means what?
Must be asking.
Well, remember, in order that means and if one of them goes off to infinity and the other one goes to zero, then it does not have a limit. And in fact, is infinity to the one to the infinity doesn't exist. It's not a mistake. So yeah, 1 to the infinity is an indeterminate form.
It has.
Hmm?
In order for something to exist, it has to be graphable.
No, not necessarily graphable. I mean, a point is not technically graphable. It's only, we use a cartoon of a dot to represent it. All right. So, one thing I will say about L'Hopital's rule is that occasionally you have to use it more than once. Okay, so are not indeterminate forms, but kind of sort of look like these. If I get 0 over the infinity, if I take this limit, if the limit goes to this, then what is this equal to? Where would we say this goes? So my numerator is going to 0, my denominator is going to infinity. What is the value of this thing going towards?
0?
Right, because if my denominator is exploding, then this thing is getting really, really tiny because of its denominator. And also because of its numerator. Both of them are driving this this value to 0. Okay? Infinity over 0, well, my numerator is exploding, and my denominator is shrinking. So again, both forces are pushing this guy's value up. Okay, a small denominator makes it huge, a large numerator makes it huge, they're both helping out, this guy goes off to infinity. All right. Now, infinity minus infinity, which was an indeterminate form, there, who says which infinity is bigger? Okay, like there's the smallest infinity is called Aleph null, and I always screw up the symbol for it. It's if anybody knows. Well, several Middle Eastern languages use the same numeral system, but Aleph null. Aleph is the first letter of the Hebrew alphabet. I believe it's also the first letter in the Farsi alphabet. I could be wrong on that one, but I know it's the first letter in the Hebrew alphabet. and it looks like a weird looking N. But Aleph null, it looks something weird like that. I'll have to look it up. It looks like a weird looking N. I'll look it up. Yeah, there it is. That's the symbol.
What? How do you write this?
I would say
Small numbers.
the bar and then 2 markings above and below. Okay. That one's probably the easiest to draw, or this one gives an explanation. Straight line and then 2 side marks. But anyway, Aleph is the smallest infinity. And Aleph null is the infinity associated with the this is the size or the cardinality of the natural numbers. Well, the natural numbers are infinite, but so are the integers. And the integers have more numbers than the natural numbers do, because there's positive and negatives in the integers, right? Whereas the natural numbers only have positives. So we have 2 different infinities, but of different sizes. So if we have an infinity minus an infinity, who's bigger? Is it positive? Is it negative? Is it infinite? Is it finite? What do we know? We don't. It's not 0, probably. You know? So it's not like we can play with this. And finally, 0 times infinity, again, that kind of goes back. One thing is getting bigger, one thing is getting smaller. What is the result? Okay? You know, and we've seen these before when we dealt with other functions where one guy goes up, one guy goes down, and somewhere in the middle is the product. Or some hybrid of the 2 is the product. All right. So, let's do some examples. Okay. Classic. Natural log of x over x. Okay. So, first thing you always try and do is plug it in. See what happens. Okay. Well, the natural log of a number that gets really, really big. Well, look at the graph of the natural log. Does it get really, really big? Does it get really, really small? Where does it go?
Natural log, that makes like.
You have to know these curves, people. If you don't know these curves, you're in deep trouble.
So they kind of look like square root function.
Sort of kind of looks like it, yeah. Is it? And it's growing, right? It increases all the time. All right. It never loops back down or anything like that. And this guy goes off to infinity. And we want to be careful here that we're not saying it equals, but instead that it goes to, okay? Because remember, you can't ever equal infinity. And we also have infinity, and x, as we go to infinity, again, goes to infinity. So we have infinity over infinity. So we have an indeterminate form. And it's in the rational form that L'Hopital's works in. So what we do when we do L'Hopital's rule is to take the derivative of the top and then take the derivative of the denominator and look at that limit. So this is what L'Hopital's rule does. L'Hopital's rule is when you have this indeterminate form, you apply the first derivative to the numerator and the denominator separately. This is not the quotient rule, okay? Which I'm sure we all remember, right? Of course we do. So this would be, and if you drop these limits, I will skin you alive. Yes. So the derivative of the numerator is, yes, 1 over x, very good, yes. And the derivative of the denominator is that. So now we have and this goes to, yes, 1 over infinity goes to 0. Is it me or is it like setting on London broil in here?
Yeah.
Is it warm?
Okay, yeah, it's really
Much
hot.
agree.
Is it getting warm? All right. So again, you attempt to plug in and see what happens. Because just because you get a 0 in either the numerator or the denominator, or infinity in the numerator or the denominator, and not an indeterminate form, that does not apply to L'Hopital's rule. So like, for example, if this thing, which it doesn't, but if it did, if it went to that, okay, what does this go to? 3 over 0. Where does it go? What's the limit approach? The denominator goes to 3, the numerator goes to 3, the denominator goes to 0. Where does it go? Denominator's getting smaller, so it does blow off to infinity. Okay? So this would diverge, right? So, but it doesn't. Now, like I said, you only use L'Hopital's rule with an indeterminate form. 0 over 0, infinity over infinity. That's it. Game over. Only once. Okay? So plugging in 0 tries to go to e to the 0th minus 1 all over 0, 1 minus 1, 0 over 0. We are in an indeterminate form. We can use L'Hopital's rule. And now we go ahead and take the derivative. So the derivative of the numerator becomes
E to the 2x plus 2 minus nothing.
and the denominator is 1. So now when we approach 0, I wind up with 2 times e to the 0th, or just 2. No, it goes to 2.
Oh, so the approach is
It approaches 2, and the limit is 2.
okay.
Okay. Actually, I'm going to go to negative infinity, if that's all right. So I'm approaching negative infinity. My numerator goes to, and the denominator to infinity also. See, we wind up with this guy infinity, and then e to the positive infinity would still be in positive infinity. So again, we're dealing with an indeterminate form. Okay? So now we apply L'Hopital's rule, because we can. All right, no problem. Now what happens? The numerator still goes to negative infinity.
Almost.
Infinity over infinity, and we're still in an indeterminate form, which means we use L'Hopital's rule again. Okay. Now when we apply the limit, my numerator goes to just becomes 2, and I have e to the infinity, and 2 over infinity goes to what?
0.
0, right? Because my denominator is exploding. My denominator is getting huge. This number is going to become extraordinarily small. Okay? So this limit is 0. Okay. Now sometimes you have to do a little rearrangement. Okay, so right now we have a product. And e to the negative infinity would go to what? E to the negative infinity. Well, the negative exponent means that it's getting smaller, right? So e to the negative infinity would go to 0, and the square root of infinity would be still infinity, right? So because as far as we know, infinity is bigger than 1, so yeah, it would go to infinity. And we wind up with the indeterminate form 0 times infinity, which is not one of the forms that L'Hopital's rule is allowed to use. So what we have to do is we have to do some little bit of algebraic manipulation in order to get it into the form that we can use. How would we do it? Right. So a little bit of algebraic manipulation. Sometimes it's a bit more complex than that, and we'll do a few of those. But now you see that we have infinity over infinity, and we can apply L'Hopital's rule. And now we get 1 over 2 square roots of x times 1 over e to the x. Okay, well, now what? So we have this weird product in my denominator. And if I apply, sorry, if I take my limit now, what do I wind up getting? Yeah, you wind up again, I mean, your numerator is still 1. It's always 1 in this case. But my denominator, even though I have infinity times infinity down below, which is bigger times bigger, right? Something big times something big, which is still big. And this guy goes to, which is what? 0. Okay? Okay. Here's a neat one. Do we recognize that? What? Yeah, we just covered this the other day again, right? This guy goes to what value? No.
Oh, 0? Yeah.
Come on, guys, we did this the other day. We were talking about exponential growth and decay. This was like one of the most important things we covered that day.
Goes towards.
It goes to E. Thank you. Okay, so manipulations we're about to do right now had better get us to E because we know that that's what its value is. Okay, I mean we've done that algebraically. Okay, so if we do this, we're going to wind up with 1 plus 1 over infinity, and 1 over infinity goes to 0. So I have 1 to the infinity. See? That's not a lot of fun. It is an indeterminate form, but it isn't the indeterminate form that we can use L'Hopital's rule for. So what we really need to do is we need to figure out a way to get that x out of that exponent. How do we do that? Okay. So whatever this thing is that we don't know what it is. Okay? We'll just put it out of our minds for a moment. But let's assume that it goes to some value. All right? And let's call it y, just for argument's sake. Okay? Now, if I take a log of both sides of this equation, okay, that limit is permeable to a log. Okay? So, if I apply that, now I use my exponent rules. Okay. That's all fine and well, but the natural log of, well, what does this go to? Just the left-hand side. If we were to apply the limit right now, the x goes to infinity, and the natural log of 1 plus 1 over x goes to what? Dude, don't guess. Look at what's inside it. 1 plus 1 over x. When x goes to infinity, what does the inside of that go to? The inside of it goes to what? 1, and the natural log of 1 is 0. So we have, again, infinity times 0, which does not fly. We need to get this product to become a ratio. Okay? Here's a sneaky trick. Sneaky trick. And now we're dealing with an indeterminate form. So we have the natural log of 1, which goes to 0, over 1 over infinity, which goes to 0. And again, now we're looking at the indeterminate form, but this time the indeterminate form is a form that we can handle. Now L'Hopital's rule applies. So we take the derivative of the numerator, we take the derivative of the denominator, and we wind up with 1 over 1 plus 1 over x times the derivative of the interior right? All over okay? And you can begin to see that things cancel out. And we get one. And now undoing the natural log. So there are sometimes interesting little tricks that you have to pull, algebraic manipulation tricks, to try and get it into a form that you can actually use. All right. So this is another way to write this would be now notice that this is a one-sided limit. And the reason for it is that if you are approaching it from the left, then what's happening is you're dealing with a reciprocal function. But if you're dealing with it from the right, you're dealing with it with just the sine function. So it's either cosecant on one side and sine on the other. We're only interested in the sine part, okay? So positive powers of x, or positive powers of sine of x, okay? So again, we're dealing with an indeterminate form. So what do you think we're going to use to get this guy into a normal looking thing? Guys, we just used the trick. Yeah, we used the log. You got to get an exponent down. How else do you get an exponent down? Right? Let's do it all at once. So let's call its value y, take the natural log of both sides, use the exponent rule to bring it down. Now we're dealing with an independent, now you're dealing with a multiplication rather than an exponentiation, and we use the same trick. Taking the derivative. How about this? You guys take the derivative. finish this guy up. So using pretty much the same techniques as we used last time, where we use the natural log to get the exponent down, and then do a little bit of manipulation, wind up with an indeterminate form we can. All right. Now, here's the one that always scares me. Yeah, scares me. What is this? So plug in 1. What do you get? What's 1 over 0? What's 1 over 0? Infinity. Infinity minus infinity, which is an indeterminate form. This is not one that we can use. So what must we do? We have to do a little manipulation, mush it all together, and try and get it into a single rational function is right. So, common denominator. So, what happens to my numerator now? Numerator goes to 0, and the denominator goes to, in fact, yeah, it goes 0 over 0 again, so we have an indeterminate form. So let's apply L'Hopital. Now, what is in my denominator? Product rule. What happens now? Apply your limit. So my numerator goes to 1 minus 1 over 1, 0. And the natural log of 1 is 0 plus 0. So guess what we have to do again? It's not La Hospital. I'm going to send you to the La Hospital. All right. All right. So try and do a little rearranging on this guy to try and maybe make it look a little nicer if possible. Okay. There is some algebra throughout this thing that we can try and use. All right. So let's see what we have. Not a lot, but a little. Okay. I use distributed. All right. So again, let's go ahead and take L'Hopital's rule. And we wind up with and now what do I wind up getting? Plug in 1. Right, it's 2. Very good. Excellent. Well done. Gosh, you guys are on the ball today. Woohoo! Plugging in 1. Man. Champion one pluggers. Man. Should introduce you to my Algebra 1 class. They can plug in 2. Yeah. Sometimes they can plug in 1. Okay. So, we see how this works? Sometimes it takes a little bit of rearranging to do it, but it's not the end of the world. And in fact, they're kind of fun. All right, you know. All right, so this episode of the Bronco Show has been brought to you by L'Hopital's Rule and the Indeterminate Forms.